So let's say that we have the expression a squared minus b squared. Well, it turns out that this is actually factorable, and it will factor into a plus b times the quantity a minus b. And we can use this fact in order to factor expressions that look like a squared minus b squared. In other words, expressions that are the difference of two perfect squares. So let's go ahead and take a look at an example. And let's say that we have x squared minus 16. The first thing that you should notice is that x squared is a perfect square, and 16 is a perfect square. And this can be written as x squared minus 4 squared, which looks very similar to the a squared minus b squared form that we have above. So we can actually use this technique in order to factor this expression. So this will now factor into x plus 4 times the quantity x minus 4. Let's go ahead and try that again with another example. So let's say that now we have x squared minus 81. Again, you should notice that x squared is a perfect square and 81 is a perfect square. For this can be written as x squared minus 9 squared. And now we can fall back on that factoring technique and say that this is now equal to x plus 9 times the quantity x minus 9. Let's go ahead and dive in and take a look at a few more examples. So here on the left we have 4x squared minus 9y squared. And this looks a little bit different than the examples that we had in the previous slide. But in fact 4x squared and 9y squared are perfect squares, because we can write 4x squared as 2x quantity squared, and we can write 9y squared as 3y quantity squared. And this looks similar to a squared minus b squared like we saw before, so we can use our factoring technique. So this will now factor into 2x plus 3y, 2x minus 3y. Now let's take a look at the middle example. This doesn't look like the examples that we've had before, and one of the reasons is 8 and 32 are not perfect squares. But what you should notice is that they do have a common factor of 8. So let's go ahead and factor out that common factor of 8. And on the inside that will leave us with m squared minus 4. And you'll notice that what we do have on the inside, m squared minus 4, is actually a difference of two perfect squares. So this can be written as 8 times m squared minus 2 squared. And now we can use our technique. So this will now equal 8 times the quantity m plus 2 times the quantity m minus 2. And it should be important to point out that since multiplication is commutative, these factors can be written in any way that you'd like. For example, this is equivalent to 8 times the quantity m minus 2 times the quantity m plus 2. So in the last example that we have on the right, we have a cubed minus a. And again, neither of these terms are perfect squares. However, they do share a common factor of a. So let's go ahead and factor out that common factor of a. And on the inside we'll end up with a squared minus 1. And you'll notice that that on the inside is a difference of two perfect squares. So this will now factor to a times the quantity a plus 1 times the quantity a minus 1. And with practice, this factoring technique actually becomes very, very quick. You'll be able to look at these expressions and be able to determine if they factor and what they will factor to. Now, a word of caution before we continue to the last example. This technique cannot be used to factor a sum of perfect squares. So, for example, if we have x squared plus 4, or x squared plus 81, or m squared plus 1, none of these expressions are factorable because they are all the sum of two perfect squares. So as tempting as it may be, if we see a sum of two perfect squares, it cannot factor. This technique only works when we're factoring the difference of two perfect squares. So in our final example, we're asked to factor completely the expression x to the 8th minus 1. And this looks a little bit strange, but the first term is actually a perfect square because we can write it as x to the 4th squared. So this is x to the 4th squared minus 1 squared. And now we can use our factoring technique. And what you'll notice in this example is that we'll use that technique several times throughout the problem in order to factor x to the 8th minus 1 completely. So now this will factor to x to the 4th plus 1 times the quantity x to the 4th minus 1. And our first factor can't go any further because it's the sum of two perfect squares. But the second factor can, because it's the difference of two perfect squares. So we can actually factor this further. Our first factor is along for the ride, but our second factor will factor to x squared plus 1 times the quantity x squared minus 1. And now we have x to the 4th plus 1 times the quantity x squared plus 1, and neither of these factors will reduce any further because they're the sum of two perfect squares. However, we do have one factor that will reduce further, x squared minus 1. So now we can write this as x to the 4th plus 1. Again, these guys are just along for the ride. And our final factor will reduce down to x plus 1 times the quantity x minus 1. And if we look at that answer, you'll notice that there's no factor that can go any further, therefore we've completely factored x to the 8th minus 1. So I hope that you've enjoyed this video, and I hope that it's been helpful in learning this factoring technique. So I would encourage you to review the video and to come back to the Park University YouTube page in order to see more math videos and to get more help. Thank you.